So can you access my Colab? Okay, perfect. I will wait for Sami to send the Colab and then I will start the session.
I think you can just begin because it might take a minute more. So
okay. So I would just be I would just start my part first. So hi everyone. Today I will introduce you some EDA. Wait a second. Some pre-processing technique for DICOM images. And for this tutorial, I will use some DICOM images extracted from a Kaggle competition. So first, you need to import some important libraries such as PyDICOM, so to load and do some stuff for the DICOM images. And then you also need to load need to import the CV2 library, which is image processing library and has a lot of function that will help you facilitate the pre-processing step. So this part is just important libraries. And then you need to clone my GitHub repo because I download a small version of the DICOM images and save it there. So for the EDA part, this one is just to prepare some metadata for the training purposes. So this is the data frame in which you are provided with the site ID, which you don't need to focus on a lot at this point. You only need to focus on the patient ID, the image ID, the cancer, because the cancer is the target of our analysis. Oh, actually, I just need to start. Okay, so here I list some columns that we need to focus on: the patient ID, the image ID, laterality, which is either the left or right first. The view, you don't need to focus on that too much at this point. And the cancer and 0 stand for non-cancerous images, and 1 stand for cancerous images. And this is the distribution of the targets. So again, every time you receive a data, you need to analyze and see the distribution of it, and like to have a deep understanding of your data before you perform any type of reprocessing or analysis. So the distribution of targets, you can see there's a highly imbalance between the class 0 and class 1. In this case, there's 174 images that belong to class 0, which is non-cancerous images, and 52 images belong to class 1, which is cancerous. And for this, for further analysis, you're gonna need to do some upsampling or downsampling to make sure that your data is balanced, because the model, so that the model can train better. So this is the DICOM, still loading. So for the DICOM images, I assume that you know some of the you know about the metadata of the DICOM images from previous weeks and tutorials. So I just briefly go to it here. For the metadata, there's a few variables that you need to focus on. The patient ID, the rows and column stands for the height and the width of an image. Window center and window width, which will come handful later on if you want to apply some windowing techniques for that. And then the pixel data. This is the important part because you want to load the pixel data and visualize it. And you're gonna do a lot of pre-processing stuff on the pixel data. So for the, let me see if it's loading correctly. Yes. Okay, so I will show you the structure of the data set. So you're gonna have each folder here represent one patient, and each patient gonna have at least 4 DICOM images, and those 4 DICOM images represent like the left press or the right press with different views. Okay, so next, second. So here I will just because there may be more than 4 images for each patient, I will just assume each patient has 4 images to better like visualize a sample for you. So here, so remember earlier you used the PyDICOM libraries to read the DICOM images, and then to access the pixel array, you just need to use DICOM.pixel array to access it. And after that, you need to, normalize the images before plotting it, before visualizing it. Okay, so this is one patient. They have 4 images. They have all 4 images. These first 2 are the right press with CC or MLO views. These 2 down here are the left press with CC or MLO view. Okay, next, you want to group those lines into a function so that you can better use it in other classes or in other methods. So I group it here into this get pixel function, and this function extract pixel from a DICOM file and use standard normalization. The standard normalization I talk about is just to divide it by the min max value of that pixel data, and then you convert it to the 8-bit. The second function is to apply windowing on top of the normalization function. So for the windowing function, you're gonna just use the apply windowing because they already written all of the they already implemented all of them in this function. You just need to use it, and then you just normalize it as usual, and then return the pixel data. Now I will declare 2 variables, the pixel variable, which only contain the normalized pixel data, and the pixel with windowing, which contains the pixel with windowing data. And now I will visualize these 2 images to give you Yes. So the applying windowing is gonna, if you see, it just save memory. You want to save memory first because you want to have a fast prototyping for your model. Okay, so if we go back to the DICOM metadata, you're gonna see the window center and window width here. And the applying window in gonna help you like have a, it's like one of the pre-processing technique that help you visualize the DICOM image better. For yes, so here on the left side we can see the standard normalization, and the right side you can see the normalization with windowing, and you can see that on the left image the tissue are denser than the right image, and this is the result of applying windowing. You will get a clearer structure of the image, and with it will help you, it will help the model recognize the area of interest better. Now, after windowing, I will introduce you to a cropping function. As you can see, this image has a lot of background. For example, for the right press, it has a lot of unnecessary information right to the left side. So you want to crop. So the point is you want to crop the press area so that your models don't need to train on unnecessary data. Okay. So for the cropping function, I use the ASU thresholding after Gaussian filtering. The Gaussian filtering is just to reduce some noise in your image. And the ASU thresholding is basically divide your image into kind of like binarize your image into it's either 0 or 1 kind of thing, and it will help you like, for example, if you apply the ASU thresholding here, you're gonna see the press area gonna be represented by 1, and the black area gonna be by 0. And after that, after that, you're gonna select those area with 1 to crop it. So this is what the function does. So this is the visualization of the cropping function. Just need a second to load. Okay, so yes, so this is the red rectangle is the bounding box where the image gonna be cropped. So as you can see, you want to select this area of interest and discard the rest. And this is just to visualize the final image after cropping. So this is the final image after cropping. You can see there's no more black background. Okay, so now I will show you a simple preprocessing technique that I will just simply resize the image and save it to the dish. And as you can see, there are a lot of resolution in those images, and it's not consistent. If you want to train your model, you need a consistent resolution. So you can choose the size of your image that you want to resize to. My suggestion is to choose a smaller size to test your model first, and once you get a good idea of what your model is doing, you can try a bigger size for better result. So right now I will choose the 1024 by I will choose 1024 by 1024 to resize my image. This is just a function to read the DICOM image, normalize it, and then resize using CV2. And then you save it to the dish, also using CV2. This one gonna take a bit of time to run because it has to pre-process 226 images. The parallel function is just to, if you have more CPU in your machine, you can define the number of jobs so that it can make it faster. And after pre-processing all of the images, I'm gonna save it into the dish here. Yeah, I'm gonna save it here, and I will show you an example of it. So this is the PNG image after resizing. Okay, now I will leave you with task 1 of this assignment. So the task 1 is you want to from all of the technique I showed you earlier, you want to apply windowing, thresholding, cropping, and resize the DICOM images, and then you want to save it into your dish. So this is the pre-processing pipeline from DICOM images. Apply normalize and windowing, then apply thresholding and fine contours, and then cropping it, and then save it to dish. Okay. So I will leave it for you here to complete it. This is just a sanity check to see if what you're doing is correct. Now I will introduce another concept, which is very important for deep learning, which is cross validation. So there's a lot of strategy for cross validation, and the goal of cross validation is to help your model better evaluate your better evaluate your model performance. So in real life, you don't want to overfit the data. So you want to split the data into 3 sets, which is the strand set, the test set, trend set, validation set, and the test set. And you will only perform, you're gonna do cross validation to evaluate the performance of your model from the trend set and the validation set, and you only test the model on the test sets after you finalize everything. And here I will introduce you 3 types of strategy that we normally use. K4, which is you want to split the trend and the validation set without any with non-overlapping patient IDs. The second one is stratify K4. You want to you want your trend set and validation set has no overlapping patient ID, and you still want to remain the target distribution. And the last one is stratify group K4. Means you're gonna have non-overlapping patient ID, and the group with target distribution remain the same. However, each group will appear exactly once in the validation set. And for this type of data, I will choose stratify group K4 to preserve the target distribution with non-overlapping patient ID and groups. And normally we just do 4 to 5 folds. Okay. So this is the resource if you want to understand a bit more about cross-validation. So it's easy to apply it. You just call the stratify group K4 function from the scikit-learn library. And then just specify the number of split, and you want to set a random state for reproducibility. So for this case, I just set as 232. And this one is just to visualize the trend set and the validation set for each fold. And as you can see, there is none of the indexes in the test set appear in the trend set, and it remain the same for all the folds. And now I will leave you with task 2, where you're gonna apply K4 and stratify K4 and then try to compare why one strategy is better, or which strategy is better suited for your task. Okay, so that's conclude my presentation. If you have any question, I will leave it to the end, because I will let Sami talk about his part now. Hello?
Hello, yes.
Yes. Okay, so I will let you talk about this part. And if anyone has any question, resource. Oh, you mean the Colab notebook, right? Okay. I will stop sharing now, and
Yes.
let me talk.
Thank you.
Thank you.
So hello everybody, my name is Sami. Just going, I don't know if it's big enough or try to increase it a little bit. Okay, do you see? Okay, so I shared my Google Colab with you guys just before the presentation of me. So today I'm just going to go to some basic neural networks. Oh, what's going on? All right, sorry. So this is a very basic NLP, which we call a multilayer perceptron. This is in the family of the feed-forward neural networks. So basically, here we're gonna use PyTorch. PyTorch is a very common used library for building the neural network architectures. So we first import Torch, then we import Torch NN, and then Optim. I'm going to explain them a little bit later, and then Torch Vision for the data sets. So when you build any neural network, the first thing you have to create a class. Then you call it whatever neural network you create. Here it's MLP, so class MLP. And then you put between, most of the time we put between a parenthesis and then dot model. And then what model is a class in Python that contain a lot of methods and functions that we use usually. Sometimes you're going to see some people writing torch.nn.module, but most of the time you will see nn.module. So it's very important to put this. This is going to be the parent class here. I hope everybody here is familiar with the object-oriented programmation, because that's important. And then when you create neural network, you're going to create the functions that we call the initialization function that's in it. And you put, this is the function where you're going to put the layers of the neural networks. This is where you, the arguments in the class, but the layers in neural network. So here we need 3 layers. It's a very simple MLP. There will be the input dimension layer, the hide and dim, and the output dim. So this is going to be our class. So you begin always with neural network. You begin with a super, which means that you're going to inherit from the class of NN model, and then you put MLP and self. Most of the time, you will see in neural network you will not have MLP self, but it's also a good practice to write it, and then you write .in. So now we have inherited from the NN model class, and now we're going to create the self arguments of our layers. So the first layer is the input layer, is self input, and then you use this function NN layers that coming from the NN model libraries, and you put the input features. You only have, most of the time, you have 2 arguments: the input features and the output features. So here it is input dimension and hidden dimension, because after that it's a hidden layer. And then you need to add non-linearity. By definition, most of the neural networks are linear functions. So in order to avoid mathematical problems, we usually add non-linearity. Usually we see the most common one is ReLU, but we can add other non-linearity like a time function, or sometimes a leaky ReLU or other functions. But here we added a ReLU as most of the time. And then we had another hidden layers like self-hidden, and then we had our feature. The input feature here is going to be the hidden dimension, and the output feature is going to be the hidden dimension also. And then the final layers is going to be, we call it self-output, and also with the 2 input features and output features. So this is a typical, very simple neural network. And then what is very important when you build a neural network is to add a forward function. So here in the forward function, you just take up all the arguments that you have instantiated and you put them to build your forward. Because a neural network, there is a forward pass. You go through all your function when you forward pass, and then there is a backward pass. You go back, and this you do a gradient. We'll see that a bit later. So in the forward here, we put our input, self input equal out, and we put the X here, which is our data. Will be our training data, and then we add our ReLU function, self ReLU out. We should take it out here, and so on. Okay, self hidden out, self ReLU out, self output out. So you take all the arguments and you put them all together here, and this will return our output, which is named out here. Okay. Now after that, there is we always, as in machine learning, we always add some random seed. Here we added the random seed of 42, but it could be any. Sorry, I'm just having some issue going down. Okay. So it's just to add a seed of 42. I hope everybody is familiar with that. But we usually, it's a common practice in machine learning just to create a random seed, to have always the same randomization for our operations. Device equal torch device. This is very, very, very common because usually you will train it whether on GPU or CPU. So here we define torch device. If we have a GPU, so it will go on the GPU, else it will go on the CPU. CPU usually is on the computer or local, and GPU, it can be also on the computer or on if you have a supercomputer or else or Colab, gonna be there. And then usually you have transformation, mainly when you have image classification and so on. But here we're gonna do some more transformation. We're gonna transform our data into tensor because our data is not tensor, and then we're going to normalize it. This is also very common practice. Then here we're gonna download the MNIST dataset. MNIST dataset is very common, famous data. It contains 10 levels from 0 to 9. This is basically to classify. It's a multi classification problem. So we use this in image classification. So here we're bringing it from dataset.mints, and then we load it. Whenever you do a neural network and we're gonna train it, you have to put it on a data loader because you train it by batch. Here we define a batch of 64, but it could have been another batch, or we can try a different batch. And then here we're going to instantiate our MLP model. Here we're gonna give some shapes. So the image, since the image of MNIST are 28 per 28, the input dimension is going to be 28 per 28. The hidden dimension is going to be 128, and the output dimension is going to be 10. One of the biggest challenge when you're going to build a neural network is to fix the shapes. And usually, whether you have you will have a data set and you will have to fix the shape of your neural network in order to adapt to your data set, or the contrary, you will have a neural network that has been pre-trained, and you will need to fix the data in order that it get into the neural network. So here we have the data, and we're trying to fix the shapes of that will get into the neural network. Here, so now we instantiate the MLP, and then what's very important is the loss function. Since there is many loss function, but since here we have multiple classification problem with 10 levels, here we're gonna use the NN cross entropy loss. So this is very typical one for multiple classification problems. And then we need an optimizer. So the optimizer here is defined as Adam. It's a very common one also. And we choose a learning rate of 0.001. Typically, when you're gonna do you're choosing after that in the validation the best parameters and the optimizer, you will try different optimizer and different learning rates. But here for now, for the first experience, we just use those ones. And then, yes, and then this is the most important part. When we put everything together, this week, what we call the training group. So first we define the number of epochs, and then you iterate the number of epochs. And for each epoch, you want to train your model. And then after that, you batch, you iterate over the training batch. So here, for example, for batch and index, and then you go on the train loader where you have your data, and then you go to your device, which is going to be here the GPU, and same for you put also your labels on the GPU. So now you have your data and the labels on the GPU, and then you do your forward pass. You go use the function that we create before. And then you after using the function, you do your loss, where you put the output of the forward and the labels, and then after that you do your backward, or what we call the gradients, the computation of the gradients. So you do it with the optimizer, with the loss, and also by using some steps. So this is in mathematics. This is basically a diagnostic differential calculus, but maybe we're gonna see it later in this class. So after that, you print for each epoch, you will have your results and your loss. Yes, so this is a very typical and very simple neural network that has been trained on a very typical classical data set, which is MNIST. And then we're gonna do the same. Usually you need a train, a valid, and a test, right? But here we just for this example, we just, since we're not making validation and post-validation, we just using a train and a test data set. So we do the same for the test data set once the model has been trained and has been saved, of course. We take the model that has been saved and we train it on the test data set. And it's exactly the same that what we did. It's just the data that is changing. And so after that, we have an averages and an accuracy. What's the difference between the train and the test is that the test is a small amount of data, but that has not been trained. And so you can test the generalizability on it. Which means what we mean by generalizability is how to deploy it in real life when it's going to be faced to new data that the model has not been trained on. Right? So this was very simple. Now I'm going to let you do some exercises. Maybe some will find it a bit difficult, maybe not. So it's a CNN, it's a little bit more complex neural network. You just have to fill the blanks with the shapes that I'm asking on the exercise, and then we'll correct it. This is for exercise 2 and exercise 3. Same for exercise 3, it's an autoencoder. So I will leave you with that. And maybe I'll give you a few minutes, 5 minutes, and we will continue. Okay.
Thank you, Sami. So yeah, if anyone has any question, we can answer it now, or you, yeah.
If anyone has a question on the exercise, please feel free to ask it. Otherwise, in a few minutes, I will correct them.
Hello. So if there are no questions, we can leave you with the assignment, and if yes, and you can work on them. If you have any question, you can always get back to us on the MacMed Discord, and we will try our best to answer those. Yeah, so Sami, I think it's better to let them work on the assignment first, and don't give them the solution yet.
Yes, I think it will be more beneficial that you work on it and take the time to fill the blanks, even if it's not building an architecture from scratch, but you still have to focus on the scratch on the architecture, sorry, and try to fill the shapes. and take the time to do the exercise properly, so you might understand better. And then after that, I think we can see the solution. Yeah.
Okay,
Together.
so for anyone who joined late, let's share the collab links again so that they can access the assignment.
Okay, I'm gonna share. You want me to share again?
Yes, yes, because someone asking that.
Okay, it's done.
Thank you, Sammy. Yes. Okay, so we can end the tutorial session now. Hope you have a nice weekend. Hossein, just a question, will the recording be available? And yeah, we will work on the recording and see if it's gonna be available for you. Okay. So for anyone who joins late, this is the this is the end of our tutorial session. We're gonna give you the recording after this on YouTube and Gumroad. Yeah, I will just wait here in case if anyone has any quick question. You can go, you can leave.
You can also ask question on Discord if you have a question later. I should check my Discord regularly for the, you know. Mm.
Okay, Sammy, do you want to end now or you want to wait? I think I'm
Yeah.
gonna leave now. Okay,
Yes, I think we're gonna leave them with the tutorial, and yes,
okay.
yes.
So see
So
you.
see you. Thank you very much, and you. Thank
Thank
you,
you.
everybody. Very day.
Bye.